Hello. I'm very excited to be here at Nullcon. First time here in this conference. So I guess while people finish entering the room, I'll start kind of saying, basically, what I'm going to talk about today is Android security or Android vulnerability research. I'm going to basically describe some sort of vulnerability that I found and an exploit I wrote for it, which I don't know how many of you follow closely the Android exploitation world, but I feel is a bit unique in a way because I'm using an Android component that is called the TrustZone in order to exploit the kernel, which, I just thought is kind of nice. So before I go into the details, a little bit about me. I started my kind of career in cybersecurity in the Israeli military. I did I worked a few years as a vulnerability researcher in a company called Imperium. I did actually just finish about a year and a half stint in something that was not cybersecurity, and I pretty much will go back to cybersecurity next. And also maybe one more fun fact about me that this is my first time at Nullcon, but definitely not my first time in India. I've traveled like multiple times, spending maybe overall about 6 or 7 months in India, and I think like covering maybe 9 or 10 states and counting. So Okay, so let's go into the details. So what will I talk about today? So maybe a good place to point out that I'm never sure how to completely structure these exploit talks because you as an audience, you're kind of expected to delve very quickly and very deep into some very technical details. I'm trying to do it gradually. So I'll start with some brief background information about what the TrustZone is because I don't know everyone's background here. I will go then into more details about the communication protocol around the Qualcomm TrustZone, because you will see that there is where the vulnerability is. So we'll have to explain some more technical details around there. I will also then, of course, describe the vulnerability that I found. That part, I imagine, would be quite short because it's basically describing a bug. And the longer part will be the exploit, which I guess, like every vulnerability and exploit, the exploit is always complicated. And unfortunately, I won't even have time to cover every tiny detail of the exploit because it just doesn't fit in a talk like this. But all I can say is that I am planning to release very soon, probably in the next few days, both blog posts describing my research with the full details and even the source code. So if you want to see everything, all the tiny details that I kind of skip here sometimes, you will be able to see them. And then I'll finish with some takeaways from this research, which I think are interesting. And even though that what I find that this exploit and vulnerability are a bit unique compared to other exploits, I still think talking about them in connection with other Android and general exploitation techniques and mitigations, I do think it's interesting. I say that people are still entering, so maybe I'll wait a moment. So let's start with some brief overview about what the TrustZone is. So for those who don't know, maybe if you haven't really worked or looked into Android before, basically in Android, in every Android phone, you have, alongside the Android operating system, you have another operating system that is called the TrustZone, which is basically higher privileged operating system. It is used for mostly things around cryptography, like for example, DRM, right? So you'd have like Netflix and they send you encrypted video file, but you still want to play it on your device. So the component that has access to the raw keys to decrypt that media is the TrustZone. And only the TrustZone can play that video on the device. And this way, Android is not accessible to the keys directly. So as I said, it is like in this way, in this separation of components, it is higher privileged. So really more privileged than the Android kernel, more privileged than kind of anything in Android. And what I think is interesting here is that it is closed source, or like it's almost always closed source. And then if you think about it, you have on your phones some other operating system, like a full operating system, which is like higher privilege. And unlike Android, which is mostly open source, this one is completely closed source. And yeah, I think for me, that was like the first kind of motivation of doing this research, because I just thought that it would be interesting to look into this. Probably also a good time to point out that what I'm presenting here, I just did on my free time, right? I talked about my experience before, but this was kind of just stuff that interested me to look into, and I happened to find this and exploit this, so I'm not coming here with any secret agenda. So yeah, okay, so this is the Android TrustZone. So what about I mentioned in the title of the talk, right, the Qualcomm TrustZone. And the truth is that in Android, every chipset vendor, which the main ones would be Qualcomm, Samsung, Huawei, and MediaTek, they kind of implement their own, or not kind of, they implement their own TrustZone. And I mentioned the TrustZone is its own operating system. So you have just different operating systems, completely different between each chipset vendor. So I did my research on Qualcomm, which they call their TrustZone QC or QT, you can find in some places. I think someone in Qualcomm told me that they renamed it once to QT for marketing reasons that I don't understand. I'm still going to use QC just because that's what I'm used to. And this is also the slide where I try to kind of show that Qualcomm has a big deal of a market share. I don't think it's the best. I really couldn't find that good data, but like this. But like the bottom line, that really, especially if you look at like high-end Android phones, Qualcomm by far has the biggest market share. So interesting to research. And then I said, okay, so we have this higher privileged operating system running alongside Android, and each chipset has their own. So what prior research has been done into this Qualcomm one? And the truth is that personally I feel that this research into QC is kind of rare. There was a very thorough set of blog posts by Galbin Yamini, but they're kind of old by now. The last one was in 2016. And since then, I always try to find other public research at least, and it's very, very rare to find, which I guess in a way was also a motivation for me to do this research into Qualcomm TrustZone. So yeah. So sorry if it's a bit of an intimidating slide. This is kind of the general idea of what the TrustZone is. Like I said, you have this other operating system that is called like the secure world. So it's like running with higher privileges. But this is something you'll find, if you ever saw a presentation about TrustZone, most chances you saw something like this. If I narrow the components here to the relevant parts to my talk, it looks like this. And basically, if you think about it, we have this higher privileged operating system, right? Or like I gave the example of DRM. So we want to play encrypted media, but the encrypted media would still be in the Android user mode process, right? So it needs this API to communicate with the DRM code, basically. And so this communication kind of goes over multiple layers, as is shown here. Probably good to remember some terms here, like for example, the user mode process on the TrustZone side is called the trustlet. So I'm going to use this word a lot. And then on the Android side, for this communication, a kernel module that is called QCCOM is used. So let's say an Android user mode process wants to send a command to a trustlet, it would send a command to this kernel module, and the kernel module basically does everything that is needed to be done on the Linux kernel side. So yeah, I think the QCCOM and trustlet are words I'm gonna repeat quite a lot, and of course QC. So yeah. Okay, so this is basically the Qualcomm TrustZone. Yeah, I'll go into a bit more technical details. Maybe before that, I do want to preface my talk a little bit. So just like full disclosure, this is not like a complete full root vulnerability because you would need access to the QCCOM kernel module, which traditionally is not accessible by regular apps. I can say I have in the past also released an exploit to get access to this kernel module. But yeah, I'm not coming here to basically show, oh, look at this amazing vulnerability, like you can hack all devices with it. It's more like I'm talking about kind of different and unique exploitation techniques and their implications in general to Android security. And of course, this would only work on Qualcomm devices because, yeah, it's about the Qualcomm TrustZone. But then on the other hand, I do think this exploit is very powerful in its own way, and why I think it's interesting for exploitation techniques, because you'll see that this is a super, basically 100% reliable exploit, which is, I feel a bit rare sometimes that now in Android kernel exploitation. And not only that, the exploit that I wrote is able to basically exploit all devices and versions and builds that I tried without needing adaptation per device and build, which I also think is quite rare these days. So, okay, let's go into some technical details. And I'll start with describing kind of the memory access model here with QC, the Qualcomm TrustZone. So one very important thing to remember is that QC works in physical memory addresses, not virtual. So yeah, just important to remember. But then the way it works, because I mentioned that QC is kind of more privileged than the Linux kernel, and basically I guess I'll use diagrams to show it a bit better. So this would be the physical memory layout, right? I mean, and if we think about normal operating systems, you would have the kernel accessible to everything, to all physical memory, and each user mode process would carve out some parts of this physical memory to only be accessible to it. But now if we add the TrustZone, we see that we also have some region of physical memory that is used as secure memory, and the Linux kernel can't access it. The QC kernel, on the other hand, can access everything, and it in turn limits the user mode processes on the QC side, the trustlets, to only very small regions of their own memory. But now there comes the question, oh, but we want this trustlet to communicate with the Android user mode process. And ideally, we want this communication to be kind of efficient and not copy memory all over. So there should be a way for them to share memory just for this communication. So I'll go into that, and I'll try to do it gradually. So I'll talk about the components, and first I'll talk about all the components involved other than QCCOM, other than what happens between the user mode process and the Linux kernel, and I'll then go into that, mostly also because that's where the vulnerability is, so I'll finish with that. So yeah, let's talk about this communication between the normal world to the secure world. I'll start with the simple version, and it will get more complicated. So basically, when normal world wants to send a command, like the Android operating system wants to send a command to the TrustZone, to a trustlet, it sends something called SMC. And maybe diagrams will show it a bit better. So let's say I want to send a command. Again, it's some sort of IPC, RPC mechanism where you have an input buffer and you expect an output buffer. So in this example, I have my input buffer, right? I already wrote it to memory. And now I want to send the command. So I send this SMC. And this SMC has basically two pointers to two buffers, like each with an address and size. One is where the input is already written to, and another is where the output should be written to. And then what the QC kernel does is that it kind of opens a window, right? It gives the trustlet access to this area of memory. And the trustlet in turn can, if it's DRM, can, decrypt, encrypt, whatever, and read the data from the input and write the data to the output. And from here on, because again, this is normal memory, right? So the normal world, the Android operating system, Linux kernel is accessible to the output and can just read it. Yeah. But it gets more complicated than that. This was, kind of simple. But let's say there's a lot of input data, or we want to have some input/output data, and we want to give the trustlet a bunch of different data in different places around physical memory. And so this basically, yeah, this communication protocol supports also that. And the way it's done, that's where it really gets more complicated. That input buffer that until now only contained raw data now can only can also contain pointers to other parts of physical memory. And yeah, it gets more complicated, right? Because the trustlet would also need to be accessible to those parts of physical memory that are being pointed to. And the way it works is that each SMC can also contain up to 4 what I kind of call whitelist entries that tell basically the QC kernel which other parts of physical memory the trustlet needs to have whitelisted. So yeah, I'll show it with a diagram. So again, for example, we have this input buffer, but now it has this input buffer contains the physical address, basically a pointer to somewhere else in physical memory. So we still have this SMC, right, with an input and output, but now this SMC would also contain a whitelist entry. And we'll look into how this whitelisting mechanism works. And let's say for our example, the data being pointed into is the physical address deadbeef. So yeah, let's take a look now, because this is interesting, about the actual bytes, basically the input buffer. This is like an example. And if you look really closely, you can see that 4 bytes into the buffer, we have the address, right? So this is deadbeef. But now, like, how does the whitelist entry looks? Like, you would expect kind of the simple answer would be, oh, so the whitelist entry would just be like address deadbeef and size whatever, and then that buffer is whitelisted, but it's not like that. So the size is there, but instead of having the address, it has an offset. And what this offset is basically is offset into the input buffer of where the address to be whitelisted is. So here it's at 4, right? So what the QC kernel does here, it would read the whitelist entry, go, in this example, 4 bytes into the input buffer, read the address there, and know where to whitelist from. And yeah, this is a bit of perhaps overcomplication, perhaps some optimization to save memory, to save duplication of data. I'm not entirely sure why Qualcomm did this, but that's how it works. And yeah, from here, as I said, so now the trustlet is accessible both to where the input and output buffer, but also to this new other buffer that is being pointed to from the input buffer. Yeah, so this is how it worked. Basically, I said, right, like this is how it works for all the components from Linux kernel, QC kernel, and trustlet. But how does the Android user mode process start this, right? Like it's actually the component that starts this whole thing, that sends a command. So of course, I said it uses the QCCom kernel module. And for this, it uses something, Linux kernel mechanism that is called ION. It's something that I feel if you read some Android kernel public research, at least about Android kernel exploits before, you might have noticed, like they kind of appear a lot in these exploits, the ION buffers. And there are some complication of what it is. I'll kind of narrow it down to only the relevant parts to the talk, which is basically it's a buffer that a user mode process can can ask the kernel to allocate, and it receives back some file descriptor that it can then map into its own memory space to read and write data to that buffer. And the important thing to remember that all this shared memory that I talked about before, all memory shared between normal world and the QC and secure world is on these ION buffers, all of it. So let's say I'm an Android user mode process and I want to send a command to a trustlet. What I would do is first I allocate this ION buffer, right? And I write the input data into it. And then I send it to the QCCom kernel module via an IOCTL. And that IOCTL contains then the file descriptor of that ION buffer, as well as offsets into that ION buffer of where I wrote the input buffer into and where the output buffer should be written into. And from then on, we saw it before, right? It goes to the Linux kernel, to QC kernel, trustlet, and I talked about how it works. But then there's like, I mentioned this more complicated way of doing it, right, with pointers. And that's where it gets more complicated, because this Android user mode process needs to have a way to point from the input buffer to other buffers, again, other ion buffers. But like I mentioned, that it's all on physical addresses, right? And of course, the user mode process doesn't know the physical addresses that it needs to point to. So what it does is that in each IOCTL, other than the main ion file descriptor that you can add that has the input and output buffers, you can also add up to 4 extra ion file descriptors, each one of them alongside an offset. And this kind of tells the kernel where the kernel then writes the physical address there, and I'll show how it works. So like, if you remember the input buffer I talked about before, so like in this example, this is how it would look like before the IOCTL, how the user mode, what the data that the user mode process wrote there. And if you look closely, you see that the address deadbeef is not there, because the user mode process doesn't know what physical address the ion buffer is at. All it knows is where it wants the address to be written to. So it attaches this ion file descriptor with an offset of 4. And then it's the kernel's job to basically go there and write the physical address. And now this looks the same as before. And basically what the kernel does is kind of it converts, right, from that ion file descriptor to a whitelist entry, because the offset is the same. And the kernel knows the size of the ion buffer as well, so it just adds that to the whitelist entry. And yeah, so from then on, again, I talked about how it works. Okay, so these were like, I guess, some complicated technical information. But this is the background they needed to explain about the vulnerability. Maybe if you think really well right now, I know it's super hard, probably super hard, but like in theory, you have like kind of the details to know what the vulnerability is. So like, I guess, of course, the first idea that pops out is like, oh, I have this offset, it's supposed to be written into a buffer, maybe there's a buffer overflow if I give a too big offset or something. And I think this was actually a CVE a few years ago or something, like the vulnerabilities were there. But this is kind of simple one, right? This is actually a bit more complicated. So, but it's still something about using these offsets, right? Like the offsets you can give are different ion file descriptors in the IOCTL. So like, if we think about it, right? So we saw every physical address is 8 bytes. But like, what if we give offsets that make these addresses overlap each other? So yeah, let's look at it, right? Let's say I take the same thing as before. This time, even same ion file descriptor to deadbeef, but this time I also provide another one, but to the same file descriptor, but with offset of 8. So we saw how it works here, right? Like the address deadbeef is written here, but then when the kernel writes the second one to here, it would look like this. And then if we look at the whitelist entries, which are then this, right? And especially what the first one points to, it now points to deadbeef instead of just deadbeef. And of course, this is just like a random example, but let's say in our example that deadbeef was just, right, the ion buffer that we as a user mode process should have had full permissions to read and write to, but that deadbeef is this super important kernel memory address. At this point, the trustlet will be accessible to that, and we could send commands to the trustlet in order to modify memory there. Yeah, so this is basically the vulnerability, right? Like this whole complex mechanism of I get the trustlet from user mode, I get the trustlet to have access to some other memory that I'm not accessible to, and then I would be able to send it commands to modify that memory. So yeah, that's the vulnerability. Maybe one thing I should also note is that if you look closely, there was some side effect here, right? If you can see, there's like by the end there's like FE, 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 that this second overlapping kind of, zeroed. So ideally, to trigger this vulnerability, I would want to avoid side effects. And I did kind of figure out this. So basically, if you extend the size of the input buffer, the trustlet, no component cares like that there's more data. The trustlet will just stop reading after a few bytes. It will just ignore what it doesn't need. So what you can do is basically do all this address overlapping thing in the end, like add more data to the input buffer, do this whole overlapping thing in the end. Like here I push everything hex 20 bytes forward. And if I know what physical address then I want to modify, I can just hard code it. The trustlet will access it. In this example, I could even then modify dead beef, dead FFFF, and it would work. So, okay, so I have a vulnerability. And now the question is, how do I exploit it? And okay, this is nice, right? Like, okay, but I said it's a very random example, dead beef to dead beef, dead beef. Usually memory layouts would not be that nice. I can't just like do something that simple to access very important memory. And then I was thinking, maybe I can how can I shape different physical addresses to construct a meaningful new physical address? But it's also like a bit complicated. Remember, I have this limitation of up to 4 ion buffers per IOCTL. And I basically wanted to turn this into like a full kernel read-write primitive. So what I did is basically I read more the code. And I figured that there is one more detail that I kind of forgot about when I was doing this research, and now I intentionally omitted before, and I haven't discussed. And this detail is that if you think about it, actually memory in physical space doesn't have to be contiguous. And all I've been talking about is contiguous memory in physical space. Technically, right, this is basic operating system stuff. It only needs to be contiguous in virtual memory. And if we look at the diagram, right, like all I need is the contiguous in virtual memory. That's why one of the reasons we have virtual memory. And let's say we actually got an ion buffer that has non-contiguous physical memory. Like how would the whitelisting work then, right? You can't just whitelist a single buffer in physical memory. So for this example, let's say we have these 2 buffers in physical memory now with these addresses. And let's look how this works. And this is where it gets even more complicated. So now we have this non-contiguous ion, and it points here. And what the kernel then writes is something that looks like this. It's a lot of bytes. And if we look into it closely, we see that it's basically an array. And each entry in the array, like for example, the first entry is the first buffer, right? It has both the address and the size. And then the second entry is the second buffer. It has both the address and the size. So now the QC kernel basically knows to whitelist everything according to this array. And now the whitelist entry also, it has like some flag there that is turned on that tells QC kernel, oh, this is non-contiguous. And then the QC kernel knows that instead of what used to be size, right? There was field there of size in the whitelist entry. Now it's count, because basically the count of entries in this array. And yeah, so now QC kernel knows how it works, and it whitelists everything according to this. And yeah, this is how it works. And if you think about it, this is quite interesting, because like basically I was talking about overlapping addresses, right? But if you think about it this way, I have the size in the input buffer as well. So what happens is that by overlapping data, now I can more than just control the address, I can also control the size that is whitelisted, which is very good. And now I was like, okay, this is cool. And I was thinking, okay, so what do I want to whitelist, right? Let's say I can make this huge buffer whitelisted, and why not just whitelist the whole Linux kernel memory? Like if I could, why not? And I looked into it. There is a pseudo file in Linux that kind of tells you how the physical memory layout looks like. And I was like, okay, so this is what I want to whitelist. Good to know. And so yeah, then I started to think, so how do I whitelist this thing? And a good thing to remember is, again, we are talking about physical memory. Physical memory is not randomized. I know every time it would be the same. I know what addresses it would be at. More than that, like even the start address, it's more of a Linux ARM architecture thing. Like in all devices that I looked at, the start address was even always the same. Yeah, way more predictable and easy than virtual addresses. So yeah, so unfortunately, this is the part that I kind of have to kind of skip some details because it does get more complicated. And you know how it is in exploit. You kind of construct this mechanism in order to corrupt data in a certain way that then is corrupted in another way, and then you kind of construct all your bytes to look in the way that you want them to look. And again, you're welcome if you want to like follow me on Twitter, because I will release the source code for this exploit. So you can see exactly how it works, but this time I'll cover it very shortly. So basically, as I said, I now have this option to, by overlapping data, to control both the address and the size that is being whitelisted. So the technique that I came up with is to kind of do it and by overlapping data to whitelist everything from 0, because it's kind of easier to zero an address. So from 0 up until and the size of it would be something that I know for sure is after kernel memory in physical layout. So again, I'll show it here. I have this technique. It uses kind of 3 ion file descriptors. I have this non-contiguous one like we saw before. And then all I need to know is that this one is contiguous and its address is after the kernel memory. I mean, again, a lot of overlapping with bytes and stuff, and so I write it here, and I overlap some more thing to zero the address. And really, the most interesting thing is that like the first whitelist entry that I end up with, and really the first entry in the array, which is from address 0 to this address this FE address that I know for sure is after kernel memory. So this was really nice because I was very excited. I was like, this is what I wanted. This should be it, right? Like I got the full kernel memory whitelisted. At this point, all I need is just find some command I can send to a trustlet that would have a pointer to some data that I want to modify, right? Should be easy. And it was not easy. So basically, trustlets don't really have that simple functionality. And I have to do a lot of reversing. And the truth is that I reversed a trustlet that is called Y-Divine that deals with DRM. And the challenge there was mostly because it actually has a lot of functionality, but even just activating that normal functionality, right? I didn't intend to exploit any vulnerability there. Even just using normal functionality there is quite tough. You need to go through a lot of like APIs and stuff to make it work. And it took me quite a lot of reversing work to do it. And unfortunately, again, I don't really have the time to talk about everything. I think I can maybe make a whole presentation just about that. But eventually, I did manage to activate some functionality, which is basically like 2 different functionalities, one for encrypt and one for decrypt. But what I know about them is that they both would use the same symmetrical key. And if you think about it, if you can encrypt and then decrypt memory using the same symmetrical key, it's basically equals copy, right? It's like just a harder way to do copy. So yeah, this is enough to copy memory from one place to another. And now, finally, after I had this, I basically had arbitrary read and write, right? Because I had copy from addresses that I control from one address to another address. I have the whole kernel memory whitelisted, so the trustlet can access these addresses. So I can just send the commands to the trustlet and get read, write, copy anything from some address to some other memory that I can read or write, other way around. So this was amazing. And finally, I had like a full working exploit. I looked up, like, for example, what was the physical address of the symbol that decides if SE Linux is on or off. I changed it to 0, and SE Linux was disabled. So amazing. But then I thought, this is actually a pretty strong primitive, like read and write on physical memory. What if I don't need to look up for every build the physical address that I want to modify? And for this, I used a mechanism in the Linux kernel that is called KAllSyms. Basically, it keeps track in memory of what addresses are of all the symbols. And I wrote some code that kind of scans through the whole kernel memory to find this, to find something that looks like it, parse it, and this way I was able to, know the addresses of each symbol I want to modify. And by this point, my exploit worked on all devices and versions that I tried it on, which was super cool, without needing any adaptations. Disabled the Linux on all of them, which, I think is really, really nice. So, that's the exploit. If you lost me at some point, maybe that's where it gets a little bit less technical back. I'll talk about some takeaways from my research and how does it compare to other Android and kernel exploitation. So, why is this exploit powerful? And I think the first thing is that, again, it's super reliable, which is already a bit rare, I think, in kernel exploitation, especially with Android. And if you think about it, I never actually encountered any security mitigation exploiting it, right? Like, first of all, it is what is called like data-based, which I also think is quite a trend in Android kernel exploitation, which is basically says, okay, so we have all these mitigations that deal with code executions, but if we want to exploit something, all we need is just to modify the data, right? We don't have to run a shellcode or a ROP if we don't like. It's just like a way to get things done, but if we can just modify the data, like give ourselves root, we can also just do that. So that already kind of ignores a lot of mitigations. But then, like, for example, one mitigation that a lot of exploits have to deal with is like ASLR, right? But I worked on physical memory. Addresses are not randomized there, so no ASLR. And even, of course, I can't say I fully tested it because you don't really have Qualcomm devices with MTE. But it is this mitigation that people, I feel, in the security world love to discuss, this like kind of future mitigation, memory tagging. And if you think about it, also this mitigation is in virtual space. So in theory, this exploit should also work with MTE. And I guess the other nice thing is that like I don't need to adapt this exploit like per build, which is also nice. So so then I also looked, I was curious, like, so what other exploits there are in the Android world related to physical addresses? The ones I found were all around the GPU. Only the last one, he actually completed it to a full exploit. The first two, it was more like POC of changing some data in the kernel memory and was enough for them. All I say is that I think maybe this will become a bit more of a trend, especially as mitigations get stronger, if MT is ever fully introduced and becomes a mainstream thing. So I think it's interesting. This is what I think is really interesting. I even found like this analysis from Project Zero of some vulnerability from some exploit they found in the wild, but they didn't have the exploit, and then they were kind of analyzing. So what could be done to mitigate this, even with they didn't really know how the exploit worked, they just had the vulnerability. And what they say there is like, oh, if like it's a classical memory corruption, then probably like memory tagging would mitigate this. But it was in the GPU, this vulnerability. So then they say, oh, but if it's like granting arbitrary physical memory read-write, then basically to mitigate this, we would require further study, which I guess is another words to say that there's no really good idea of what would mitigate it. So some more takeaways that I think is interesting is like, again, like I said, I think research into QC is relatively rare. I said that QC is closed source, and while QCCOM, the kernel module, is in the Linux kernel, so it's open source, for me to really do this research, I had to reverse some parts in QC because it's a communication protocol, and honestly, the open source part is kind of undocumented well. It's kind of hard to tell what some of the stuff they are doing. So I feel that the reversing was very useful here, and I hope that maybe in this research I was able to shed some light on this communication protocol. And if any of you would ever want to research something like this, I hope it might have been interesting for you. So I think that like maybe even I really don't think I would find this vulnerability without reversing also the closed source side. Even though technically, if you think about it, the bug, the vulnerability was only on the open source side, right? The missing check was there. The closed source side did everything right. So that's pretty much it. I'll finish with one slide about the timeline of the report and the disclosure. don't know if I have too much to say about that. It's just like I usually get asked about it. So if you're curious about how it went, this is how it went. So yeah, that's it.
Thank you, Tamir. Does anyone have any questions? Alex.
Thanks for a nice talk. Is it really possible in some use case for this device to be available for the unprivileged user space? This bug was considered as vulnerability by Google, so maybe it is possible for some device, for some application to get access to this DFQC, as you said.
To the kernel module.
Yeah, this kernel interface.
I mean, traditionally, two things. First, you never know because Qualcomm is a chipset vendor, right? And they give their stuff to OEMs, and you never know what OEMs do with it, how they structure their access model and everything. And like I said, traditionally, you do have some like services running in Android user mode that have this raw access to this kernel module. And the traditional way would be that an app would send like some request to this service, and the service would send the IOCTL. Mm-hmm. I did, like, if you look, like, if you Google, I guess my name, or you look in my Twitter, you can see that in the past I also published an exploit in one of these services that basically gives you access to this kernel module. So in a way, you could like chain them together and to have like a full root vulnerability. So yeah.
Nice. And the second question, I didn't get why this kernel IOCTL allowed to set specific addresses in the kernel space from this user space application. So it looked like it didn't filter and validate the addresses which you provide.
So, okay, once again, because this part is like really, it's kind of hard, I feel sometimes, to understand. So basically, all the user mode does is provide offsets, right? It doesn't, even if it's me as a user mode, right? Because, and the trustlet on its side would know, okay, 4 bytes into the buffer, I should have the pointer, I should have an address there, the trustlet. Mm-hmm. If me as a user space processor just write directly an address there, the trustlet will not be able to access it, right? If I just write the physical address directly, it will not be able to access, because that's like the whole whitelisting mechanism. I could try, it will just fail. That's why this mechanism exists, and the only way I can make the trustlet have access to it is kind of by letting the kernel know, because the kernel is also the one that writes the address there, but it's also the one that builds the whitelist entries to send to QC kernel. And me as user mode process, I don't really have control too much about, a little, but not too much about the whitelist entries. So I can't really just write whatever. The only way I can really write whatever address I want to there is if I first exploit this whole, like I showed here with address overlapping and stuff, to make that whole memory whitelisted. But by default, the trustlet is just not accessible to most address, like to basically all addresses I would want to write there. So it's like, yeah.
So this bug can be called a logic bug, actually.
I mean, I would still consider it as some corruption, because I still like end up corrupt. Like the missing check was that they just forgot. I don't know. I would classify maybe some sort of a mix between them. Yeah, because there was like, it's not like, classic buffer overflow, use after free, all of this stuff. But it's like corruption of this like internal protocol structure that they just. The fix for this was that they added a check to make sure that no data can overlap other data from this stuff. But like, so it's like some sort of corruption, but not the classic corruption that you'd usually have in this sort of exploits.
Nice, thank you.